everyone. In today's video, we are going to talk about permutations. So this is one of those topics that a lot of my students do tend to struggle with, and I would like to take this opportunity to show you how to count. That's literally it. So let's get started. Okay, so in terms of what to expect in this video, permutation is literally just a way of counting, so we are going to learn to count. What permutation is basically ordered selections. So we're going to talk about today how to do those ordered selections with repetition, without repetition, restrictions, identical elements in a circle. So if none of this makes sense to you, don't worry, I'll explain all of them in a very short time. And we'll also look at how to apply permutations to probability as well. So we've done a couple of topics on various topics as well. Most of the topics I do will be relevant to the New South Wales Mathematics Syllabus for Year 11 and Year 12 across Mathematics Advanced and Extension 1. So feel free to check it out on our YouTube channel, or you can check it out on our website as well. Alright, so a little bit about myself before we dive in. So I'm the co-founder of Pinnacle Coaching College. I mainly head the mathematics subject. I personally teach a lot of Extension 2 and Extension 1. So I've seen a lot of exam questions. I've taught a lot of students, so I know where the tricky bits are, and I think this is one of those topics I get a lot of questions around, and the thinking behind it often is not explained very well at school, so I'm hoping to take this opportunity to clarify for you. Hope you find it useful. Okay, so what exactly is a permutation? A permutation, as I mentioned before, is an ordered selection. And ordered being the key element here. So this is in contrast to another concept called combination, which I'll cover in a separate video. So combination is, just to set the context here, combination is unordered selection, so where order doesn't matter. Okay, so it doesn't make a lot of sense unless you see a few examples around this area. So what exactly is ordered selections? So think in terms of the typical type of questions you see in this area. So you're talking about arranging things in a row, arranging things in a circle. You're talking about arranging numbers, letters, people, things. Okay, so we'll come across all sorts of things. That's generally the permutation category. In that separate video, which I'll talk about, combination is slightly different. So it's unordered selection. So you'll see questions around selecting people for committees, selecting people into groups, where the order in which you select or choose those people doesn't matter that much. All right, but that's not the focus of today. We're going to focus on permutations. All right, so the best way for me to explain how the counting principle works is to see various examples with different restrictions, different considerations. So in this first instance, we'll talk about ordered selections where repetition is permitted. All right, so in this case, we've got how many 5-letter words can be formed in which the first and the third letters are vowels and the other 3 letters are consonants. All right, so the best way to count this is draw what I call like little dashes, right, to represent the different letter positions. So we are trying to form a 5-letter word. The first and the third letters are vowels, and the rest are consonants. Okay, so the question doesn't say where repetition of the letters not allowed, so the assumption here is repetition is permitted. And in any question, you're trying to ask yourself is this: how many ways can I fill out that particular spot? Okay, so let's talk about vowels. So vowels will include A, E, I, O, U. There are 5 vowels in total. So there are 5 ways to fill these spots, yeah, because there are 5 possibilities. And consonants, it's basically the whole alphabet 26 letters minus A, E, I, O, U, which is 5. So there are 21 consonants in the alphabet. So there are 21 ways to fill those 3 spots out. And once you figure out how many ways to fill each of the spots, what do you do to calculate? You just times all of that together. And that's pretty much it. So if you put that into the calculator, so it's basically 5 squared times 21 cubed, you get, see, 2, 3, 1, 5, 2, 5 ways. Alright, so that's it. So that's how many 5-letter words that can be formed with those restrictions. Moving on. Alright, so this is another example where repetition is permitted. So in New South Wales, a car license plate consists of 3 letters followed by 3 digits. So let's again draw it out so we can see what we're working with. So 1, 2, 3, 1, 2, 3. Okay, the first 3 letters first 3 spots has to be formed by letters and then digits. Now, generally speaking, when we're talking about letters, we are talking about A to Z. Yeah, so 26. And digits, you're talking about 0 to 9. So there are 10 possible digits we can use. Did I say 0 to 9 or 10 to 9? 0 to 9. Okay. Again, we ask ourselves, how many ways to complete each spot? The question does not say repetition is no one now. In fact, it says no restrictions. So we'll just go ahead and figure out how many ways we can fill out each spot. So the first one is 26. Yeah, 26 letters in the alphabet. 26 is 26. And the second one will be 10, 10, and 10. All right, so once you figure that out, you just times all of that together. And that should give you pretty massive number, 17,576,000. Okay, so 17.5 million different ways. All right, so that's another good example. Let's take a look at one more. So this is another one where repetition is allowed. So the first one, we want to form a 5-digit number from odd digits only. So odd digits will include 1, 3, 5, 7, 9. Okay, so 5 possibilities. So in the first instance, we are trying to form a 5-digit number. So 1, 2, 3, 4, 5-digit number. Repetitions allowed, so you can use all 5 in every single digit. Times all of that together. So that's 5 to the power of 5, which gives you 3, 1, 2, 5. Part B, it goes, how many of these numbers contain at least 1 7? Now, I always say this to my students. When you see the wording at least 1 of anything, you're talking about complementary cases. Because if you think about it, at least 1 7, if you want to count it directly, is quite annoying. So you have to do 1 7. 2 7s, 3 7s, 4 7s, 5 7s, right? You have to do 5 different cases. Instead of doing that, do the complementary case, which is no 7s, okay? So what we're going to count is the complementary case first. Okay, so the complementary case is no 7s. All right, so if we don't use 7, so let's come back to here. We ditch this digit, so we only have 4 possibilities. Okay, so 4 ways to complete each digit. So that's 4 to the power of 5, which is 1024. Okay, so once we've calculated the complementary case, you take it away from the non-restricted version. So in this case, the non-restricted version is the previous part, yeah, because we're still talking about numbers formed by odd digits only, but containing at least 1 7. Okay, so therefore the answer is 3125 minus 1024 is equal to 2101. So that's how many numbers we are talking about. So numbers containing at least 1 7. I'll write the word 1. Okay, 1 7. All right, so that's it. So hopefully through the last 3 examples, you can see just some basic logic around how to perform counting. So now next up, we're going to look at what happens if you're not allowed repetition. So in this case, we've got 4-digit number. So 1, 2, 3, 4. We're trying to form a 4-digit number using the digits 4, 5, 6, 7, 8, 9. So there are 6 digits, okay? So what you need to think about is when repetition is not allowed, you have to drop the numbers, right, as you use them. So for example, the first digit will have 6 potential options. We'll use one of them, then the next one will only have 5 potential options. And then now we've used 2 of them, so 4. And then we've used 3 of them now, so 3. Okay? So you times that together. That should give you 360 ways. Alright, so I hope that makes sense. So without repetition just means you don't have the same number of digits for every single spot. You just keep dropping them, as logic dictates. So let's take a look at another example. So in how many ways can a first, second, and third prize be awarded in a class of 8 students? So you can think of this as first prize, second prize, third prize. So let's award the first prize first. So there are 8 potential candidates. And then first prize is gone, okay? 7 people left. Now, important thing, I know this doesn't say repetitions allow or not allow, but it's implied. One person can't be both first, second, and third, right? So use a bit of common sense to judge whether repetition should be permitted. And generally, when you're dealing with people, repetition should not be allowed. You can't reuse the same person for a certain spot, okay? All right, so the second prize, there are 7 people and 6 people. And that should give you 336 ways. Now, I also want to take this opportunity to introduce to you the NPR notation. So for these incredibly simple ones, repetitions not allowed, you have a certain number of spots to fill. You can also use the NPR notation to calculate. So in this case, for example, there are 8 students in total. So 8. And R is how many spots you're trying to fill. So in this case, 3. And this is a very specific button on your calculator. So if you have the standard Casio calculator, you will see the NPR button on the little multiplication sign in yellow. So I'm going to type in 8, shift my multiplication sign, 3. So it looks something like this. Okay, so it should come out 8P3. So the little button I'm talking about here, just trying to line that up. Yep. So you see the multiplication sign has NPR on it. So that's the button I have. You might have something else depending on your calculator. So anyways, put that into the calculator. It should come out the same thing, 336. Okay, now the previous question can also be done using NPR. So in this case, you've got 6 digits and you have 4 spots to fill. So a 6P4 should give you 360 as well. So that's just making you aware that such a notation exists. But to be honest, I don't use it from a day-to-day application only because it really only works for something incredibly simple like this one where there's no restriction. You just have like certain number of items and you have certain number of spots to put in where repetition is not allowed, and it's an ordered selection. Okay, so unless you fully understand what the NPR notation calculates, I recommend against using it. Just count it using dashes because the notation doesn't work as soon as you have anything more complicated than this. All right, so that is it. So what if we talk about a case where no repetition again, but this time we're using every single person, right? So for example, we have 7 people seated in a row of 7 stools. How many ways can this be done? So let's think about it. So 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7 people, so first spot will be 7 choices, and then 6, 5, 4, 3, 2, 1. So with that is an example where everyone gets a spot, and there is a specific notation for that. You don't have to put 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1 into the calculator. Imagine the pain. That is a 7 exclamation mark. So that exclamation mark is called a factorial notation. Okay, so that's exclamation mark. It's not called exclamation mark, it's called factorial. There should be a button in your calculator that looks like an exclamation mark. So again, just showing you my calculator. My one is like here. So I don't know if you can see it. So here, yeah, so you see that little exclamation mark. So that's what I need to do. So you tap in 7, shift that button for me. Yeah, that triggers the exclamation mark. Okay, so you see there's the exclamation mark. Okay, so that's it. That's 7 factorial. 5040 ways. Okay, and this is in fact, because we're using everyone in this calculation, this is an example of a permutation of a set. So if you have n people in a line, okay, so if you're trying to arrange n people in a line, so you're using everybody, it's always n factorial ways. And n factorial means n minus 1, n minus 2, until you reach 1. Okay, so that's what it means. Alright, so let's take a look at the next example. So another one without repetition, just to sort of tie in all the concepts and show you everything. So the first one, 8 runners participating in a 500-meter race. In how many ways can they finish? Alright, so in the first instance, basically you're using all 8 people, right? So you can think of this as 1, 2, 3, 4, 5, 6, 7, 8. So 8, 7, 6, 5, 4, 3, 2, 1. Alright, so that's 8 factorial ways, okay? Which is equal to 40320. In how many ways can the gold, silver, bronze medals be awarded? So this time you're talking about how many ways you can win. So it will be 8 for the first position, 7, and then 6. Or in other words, this is 8p3, which gives you 336. Alright, so that's the difference between the two instances. So permutation of a set is going to be 8 factorial, and then if you're only selecting 3 out of like the 8 to win first, second, and third, or in this case gold, silver, and bronze, it's 8p3. Alright, so let's ramp up the difficulty just by a tiny little bit. Yeah, what if people have preferences and restrictions? And that's where you have to be very careful how you're counting. So with restrictions, so in this case, in how many ways can 6 children and 2 adults be arranged in a row if the 2 adults are together? Alright, so in this first one, I'm going to show you how to deal with people who want to be together. So what you can do is what I call group the people who wants to be together. So I have 2 adults, right? And then the people who don't have to be together, in this case the children, you can treat them as individual groups of 1. Okay, so then how many ways can I arrange this? So you are arranging 1, 2, 3, 4, 5, 6, 7 things in a row. So that's 7 factorial, right? So permutation of a set. And then, now these 2 are different adults, so they could be A1 and A2. So they can swap positions. So times 2. That's it. So that should give you 10080. Alright, part B, if the two adults are not together, if they're not together, that's kind of the complementary case of being together. So what you can do is, so we can calculate this. So the number of ways, actually, you know what, I'll just write like this. Okay, so not together, it's easier to understand. It's basically the full set. Full set means no restrictions. Minus when they are together. Okay, so full set is basically arranging 8 people in a row, no restrictions, 8 factorial. And when the two adults are together, it's basically that answer there, so 10080. Put that together, you get 30240. Okay, so that's the number of ways when the adults are not together. Yeah, so everyone see how it's opposite of being together. It's basically not together. All right, so part C. Oh, this one's a little bit tricky. So at least 3 children are separating the adults. So I might need a new page for that one. Okay, this gets a little bit tricky. So let's have a look. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So let's put adult 1 here. So we want at least 3 children separating these two adults. So the adult 2 can't be in this spot, or this spot. Adult 2 can be in any of these spots. So what we're going to do is just think about the number of ways to fill these people first, yeah? So I'm going to put adult 1 in the first spot, so 1 way to place adult 1. And then adult 2, based on the restriction, can be in 1, 2, 3, 4. 4 ways to place adult 2. And then the others, so the 6 children. So let's say, let me just give you an example. If adult 1 is here, and adult 2 is here, you've got 1, 2, 3, 4, 5, 6 spots to go. So you can go 6, 5, 4, 3, 2, 1 if you like. So 1 way to put the first one, 4 ways to put the second one, and then the rest of the empty spots is just 6 factorial. Okay. Now if you're a little bit confused, I just want to show you another way of doing this, right? So let's say adult 2 is now here. It's the same idea. You still have 6 remaining spots to fill the children. So 6, 5, 4, 3, 2, 1. Okay, so hence 6 factorial. So we already accounted for different positions where A2 could be. So any of these 4 spots by doing 4 here. All right, so I hope that makes a bit of sense. So then we look at the next position. Let's say if adult 1 is here. So 1 way to put adult 1. So we're considering different cases. That's what we are doing. Okay. Then children can, the adult 2 cannot be in these 3 spots, but can be in these 3 spots. So there are 3 ways to put adult 2. And once you've placed adult 2, again, there are 6 factorial ways to do the remaining people. And then we keep going. So it can't be in these spots, can be in these spots. So that's 1 times 2 times 6 factorial. And then, all right, so that's pretty much the last one it can be. Yeah, if it gets too close to the end, you can't have 3 people in between. All right, so that's more or less it. So we have 4 times 6 factorial plus 3 times 6 factorial plus 2 times 6 factorial plus 1 times 6 factorial. Okay, and then now I have assumed adult 1 is going first, but then you can have the same situation where adult 2 is going first, so you can swap adult 1 and adult 2. So times 2, because adult 1 and adult 2 can swap. Okay, so then it's just a matter of putting this into the calculator. If this makes it easier, you can think of this as 4 plus 3 plus 2 plus 1 times 6 factorial times 2. Okay, put that into the calculator. That's 14400. And that's it. Alright, moving on. So let's take a look at another one with restrictions. So how many possible arrangements of the word journey are possible if? Okay, so let's separate our vowels from consonants. So our vowels are O, U, and E, and consonants are J, R, N, Y. So if you want the vowels to be together, so it's like similar to the previous case, yeah? If you want elements to be together, you need to group them. So I'm going to group my O, U, and E, and J, R, N, Y individuals. So we are arranging 1, 2, 3, 4, 5 things in a row, 5 factorial. And then rearrangements between the elements of the groups, so that's 3 factorial. And that's basically it, 720. Alright, so part B. The first and the last place are consonants. So let's draw this out. How many letters are there? 7. 1, 2, 3, 4, 5, 6, 7. So the last and the first are consonants. Alright, so how many consonants are there? 4, right? So there are 4 ways to fill the first one, and I've used up 1, so there's only 3 ways to fill the last one. Okay, so if you think about this, right now I've used 2 letters, I have 5 letters remaining, so the rest is no restrictions, so it's 5 factorial, or 5, 4, 3, 2, 1. Okay, so that's 4 times 3 times 5 factorial, which gives you 1440. Okay, and then the last set, might just move my display here so it's out of the way. Okay, so the consonants and vowels occupy alternate positions. So let's think about this. Because you have 4 consonants and 3 vowels, for that to happen, it pretty much has to be like this. Yeah? So we just go and think about how many ways to fill out each spot. So starting with the consonants, there are 4 consonants. So 4, 3, 2, 1. And then the vowels, 3 of them. 3, 2, 1. Multiply. So that's 4 factorial times 3 factorial, giving you 144 words. Alright, so that's it. So you can see it's building on the basic logic. Is always just asking yourself, how many ways can I fill out that particular spot? Alright, so let's take a look at another one. So in how many ways can the letters of orange be arranged? Okay, so that's suggesting there are no restrictions to just how many ways you can arrange the letters. So it means you have to use all of them. So 1, 2, 3, 4, 5, 6. So there are 6 letters in this. So you can either draw out the dashes 1, 2, 3, 4, 5, 6, or just know 6 factorial because you're arranging all 6, right? 6, 5, 4, 3, 2, 1. All right, so 6 factorial, which is 720. Alright, so part B, how many begin with an N? So 1, 2, 3, 4, 5, 6. Alright, if it has to begin with an N, one way to do that first spot, right, has to be an N. Then after that, no further restrictions. So 5, 4, 3, 2, 1. So that's 5 factorial, giving you 120. Alright, C, how many begin with an N, ends with a G? All right, so N, G, one way, yeah. Then 4, 3, 2, 1, no restrictions. So it's basically 4 factorial, which is equal to 24. Okay, so part D. In how many ways is N somewhere left of G? Now this one sounds very complicated, and I'm going to show you actually how to count it using a scenario building situation like what we did before. But I can tell you a very simple way to calculate this. If N is somewhere left of G, it's always half of full set. And the full set in this case is 720, so half of 6 factorial, which is 360. Now the reason why it's half is because the other half is the other way around. G is somewhere left of N. Okay, so that's why if you see this question, just remember the logic. One half is N is somewhere left of G, the other half is G is somewhere left of N. So how do we count this if we wanted to count it? Let's have a look. So orange, right? So R-A-N-G-E. So 1, 2, 3, 4, 5, 6. All right, so let's start with N is somewhere left of G. So if you put G here, for example, in the first instance, then N can be in any of these spots. So let's do this. Okay, one way to put G, and then 1, 2, 3, 4, 5 ways to put N, and then the other letters. So again, so let's map this out. If G is here, N is here, 1, 1, for example, then you've got 4, 3, 2, 1 to fill out the remaining letters, so 4 factorial. Okay, then you repeat by moving the G across. So G, then N has to be here. So 1 times 4 factorial, and then he. 1 times 3 times 4 factorial. 1 times 2 times 4 factorial, and then last spot is pretty much this. So the total is just 5, 4, 3, 2, 1 times 4 factorial. Alright, so that's 15 times 4 factorial, which gives you 360. Alright, so this is just a very elaborate way of doing the same thing, actually show you the counting process. But yeah, if you see something like that, I'll just get half of the full set. I'm not too keen on counting like this, but that's the logic. And you can see what I mean by the other half is the other way around. So if you put N in place of G, that's the other half basically. Alright, so far we've dealt with permutations with repetition, without repetition, with certain restrictions to consider. And the key thing about restrictions is you look at the elements that have restrictions first. Yeah, deal with their preferences first, then everybody else is just standard, right? You just put them in the remaining spots. Now, what if we have identical elements? So for example, in this case, we have an 8-letter word of repeated to be arranged in a line. So let's list out the letters. So we have R, E, P, E, A, T, E, D. So you see how E are repeated. So in any arrangement, you're not going to be able to distinguish one E as another E. So for example, the word repeated, if I swap these two E, you're not going to notice it. It's still repeated, right? So that's what we need to work with when we're dealing with identical elements. We have to sort of remove the duplication of scenarios or words, in this case, the duplication of words, because these E's are indistinguishable from each other. All right, so how do we deal with this? So if we treat them as all different letters, it would have been 8 factorial. right? If you're arranging 8 letters in a row, it would have been 8 factorial. And to remove sort of the repeated words, we divide it by, because there are 3 identical letters, you divide by 3 factorial. Okay, if it's 4 letters, 4 factorial, and so on. All right, so that gets you 6720. Alright, so moving on. All the selections with identical elements again, so mammals this time. Now this one's a bit tricky because mammals has 7 letters. So M, 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 A, A, L, S. 7 letters, but we're only forming a 6-letter word. So now you have to actually think about your calculation and how that's affected depending on which letters you decide to use or drop. Okay, so this is an instance where we have to consider cases because it really depends on which letter you don't end up using. So for example, in the first case, if I don't use an M, so I only use 2 M's, 2 A's, L, and S, then this 6-letter word would be 6 factorial on 2 factorial times 2 factorial because of the double M's and double A's. That gets you 180. Okay, so second scenario. This time, let's say we drop an A. So we use 3 M's, 1 A, 1 L, 1 S. So that's 6 factorial on 3 factorial for the triple M's, giving you 120. Third case, we drop an L. So M, 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 A, S. So that's 6 factorial on 3 factorial, 2 factorial, which gets you 60. And then finally, we're dropping the last letter, S. So it's the same thing, 60. Okay, so the total will equal to these 4 things added together. So 180 plus 120 plus 60 plus 60. Okay, that gets you, just realized I didn't do the total, 1 sec. 120 plus 120 basically, so 420. Alright, so hopefully that makes sense. So this one's more tricky because you're not using all the letters and the counting differs depending on which letter you don't use. Alright, so the last thing, actually that's not the last thing, but another type of arrangement is arrangement in a circle. So you may have noticed in all of the previous scenario we are dealing with arrangements in a straight line. So the difference in arrangement in a circle is if you are arranging n things in a straight line, so n things in a straight line, it's basically the permutation of a set n factorial. The main difference between a circle and a straight line is n minus 1 factorial is always 1 less. So I'm going to use this example to show you why it is 1 less. So for example, if we arrange A, B, C, D in a straight line, 1, 2, 3, 4, it would have been 4 ways to fill out the first one, 3, 2, 1. That's 4 factorial. Okay, versus in a circle. Now the problem with a circle is this. So 4 spots, right? Circle, well, it's round, so there's no definite start and finish. So what you usually have to do with a circle is pick a person to sit down first and set it as a reference point for everybody else. So let's say if I pick A and sit A down first, there's always only one way to put that first person down. Once you've put that first person down, then it's just business as usual. So the next spot will have 3 ways to fill, 2 ways to fill, 1 way to fill. So hence 3 times 2 times 1, 3 factorial. Okay, so that's one way to think about this situation. It's always 1 less because there is no definite start and finishing point in a circle. Someone has to sit down and serve as the reference point for everybody else. And there's always only 1 way to put that first person down. Alright, so in this one, let's have a look at an arrangement in a circle, and we've got a bit of restrictions. So we have Harry, Hermione, Ron, Neville, Luna sitting at a round table. So a bit of a Harry Potter crew here without restrictions. So we've got 1, 2, 3, 4, 5 people in a circle. So how you can think of it is 1, 2, 3, 4, 5. One person has to sit down first. So let's say Harry sits down first. One way to put Harry down, and everybody else just refers back to Harry. So then 4, 3, 2, 1. So 1 less than a straight line. 4 factorial, which is 24. Alright, so part B. If Ron sits on Harry's right-hand side, so again, let's have a look at the circle. 1, 2, 3, 4, 5. Again, I'm going to put Harry down first. One way to put Harry down. And then Ron has to sit on Harry's right-hand side. So Harry only has one right-hand side. So one way to place Ron. Okay, after that, no further restrictions. So 3, 2, 1. So 3 factorial, 6. Alright, C. If Harry sits between Hermione and Ron. Okay, so 1, 2, 3, 4, 5. Again, let's put Harry down first. One way to put Harry down. Then either side of him can be occupied by Hermione or Ron, yet in no particular order. So there are 2 ways to fill out that spot. So it could have been either Hermione or Ron. And let's say if Hermione sits down here, then there's only one way to fill that the other spot next to Harry. Okay, after that, no further restrictions. So 2, 1. So that's 2 times 2, basically 4. Alright, so finally, if Hermione and Ron do not sit together, so this is a classic example where you want to look at the complementary result. So let's say they do sit together. So H, R are together. Then I group them, and then you've got Harry, who else? Neville, and Luna. Okay, so you can think of this. So this is a complementary case, yeah? So we have 4 things to arrange in a circle. So that is 3 factorial, as we learned, yeah, 1 less than a straight line. And Harry and Ron, sorry, that's Hermione and Ron can swap. So that's times 2. All right, so this is when they are together. So that's 12. So then from here, if they're not together, if you take this away from no restrictions, so 24 minus 12, which is also 12. So that's the opposite case, happens to be the same amount in this case. Alright, so hopefully that combines that knowledge on dealing with restrictions and then putting them around in a circle as well. So you can see the main difference in a circle is someone has to sit down first, sets the reference point, and then you put in the other people as you choose, or depending on their preferences. Alright, so let's take a look at another circle question. 5 boys, 5 girls sitting at a round table. How many ways can this be done? So there are 10 people here, right? So 10 people, straight line would have been 10 factorial. So in a circle would be 1 less, so 9 factorial. Boys and girls alternate. Okay. Now the thing with alternating, 1, 2, 3, 4, 5, 6, 7. Okay, it's not very even, but that's okay. The thing with alternating is because there is no start or finishing line, so as long as you have them alternating, that's all you have to do. Whereas in a straight line, there's 2 ways you can alternate. You can start with a boy, boy, girl, boy, girl, boy, girl, or you can start with a girl, girl, boy, girl, boy, girl, boy. So there are 2 ways to do that one, whereas in a circle, there's only 1 way, yeah? That's an alternating circle. All right, so let's say a boy sits down, one way to do that first person, always. Okay, so after that, there are 4 girls remaining, so 4 ways, and then 4 boys remaining, sorry, 5, and then 4 boys remaining, 4, 4, 3, 3, 2, 2, 1, 1. Okay, so then that's basically 5 factorial, so 5, 4, 3, 2, 1, and then 4 factorial for the boys, so 4, 3, 2, 1, giving you 2, 8, 8, 0. Alright, so next one, if we have 5 couples, all of whom want to sit together. Alright, so we have 1, 2, 3, 4, 5 groups of 2. Actually, let's do it this way, it's very easier to understand. Boy, girl, boy, girl, boy, girl, boy, girl, boy, girl. So you arrange the groups first. So the groups, there are 5 groups to arrange in a circle. So 4 factorial to arrange 5 groups in a circle. Yeah, one less than a straight line. And then each of the groups, boy, girl can swap. So times 2, 2, 2, 2, 2. Yeah, 2, 2, 2, 2, 2. Swap, 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 swap. That's it. That gives you 768. Alright, if the boys sit together and the girls sit together, so group them, right? So boy, 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 girl, 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 girl. So 2 things in a circle, there's only one way to do that, really. Yeah, so it's like boy takes one half of the table, girl takes the other half of the table. That's it. Yeah, then rearrange within the group. So there are 5 factorial ways to rearrange within the group of boys and 5 factorial ways to rearrange amongst the girls. That should give you 1, 4, 4, 0, 0. Okay, so the last one, if couples sit together, but Chantel and Andrew don't want to sit together. So it's basically the case in C, but then, so I'll just take C and then get rid of that one of the groups and keep Chantel and Andrew separate. Okay, now if I calculate this, so this is arranging 1, 2, 3, 4, 5, 6. So 6 things in a circle is 5 factorial. Okay, 5 factorial, and then you times 2, 2, 2, 2, 2 to the power 4. Now, if we arrange it this way, it's inevitable that sometimes Chantel will sit next to Andrew, right? So, for example, if you arrange this order in the circle, Chantel will be sitting next to Andrew, which we don't want. So what you need to also remove from this counting is when Chantel and Andrew are together, which is basically C, right? C is when you have that 5th couple is together, so just minus 768. Okay, take that away, so 1152. Alright, so that's it. So hopefully this example is very good in terms of exploring all the different ways you can arrange things in a circle, in this case people in a circle, how to deal with restrictions when you're looking at a circle, and how to deal with groupings, right? If people want to sit together, what do you do? Alright, so let's move on. So the final thing we're going to look at in this video is how to calculate probability using permutations to count our spaces. So before we jump into probability, we have 2 things in calculating any probability. So you've got the event space and the sample space. So the event space, if you think about it, is basically the number of ways that satisfy your specific conditions. So number of ways which satisfy the conditions. And the sample space, how I think about it, is basically performing the same counting but no restrictions. So number of ways no restrictions. All right, so that's how I will think about this. So in this next example, we've got a family of 6 are seated in a row at the cinema. Find the probability that, okay, so before we even look at the question, right, there are 6 people in a row, no restrictions. So the sample space here is arranging 6 people in a row. So that's 6 factorial. Okay, so that's how you calculate the sample space. All right, so part A. Parents sit on the end, 4 children are in the middle. So 1, 2, 3, 4, 5, 6. So parents sit on the end, children sit in the middle. So there are 2 parents, so 2 way, 1 way, and then 4, 3, 2, 1. So that's 4 factorial times 2, basically, which gives you 48. The probability is 48 on 6 factorial, so event space over sample space, 1 on 15. All right, so part B, parents sit next to one another. So this time, group your parents, and then you've got your children. So that's 1, 2, 3, 4, 5 things in a row, 5 factorial, and parents can swap times 2, which gives you 240. So the probability is 240 on 6 factorial, which is 1 on 3 in this case. All right, 1 in 3 chance that will happen. All right, so next one. This one gets a little bit complicated because we are working with a lot of elements and restrictions in this case. So we've got a 5-digit number to be chosen at random, find the probability, those things. So we are trying to form a 5-digit number from 0 to 9, yeah, digits. Now let's talk about sample space first. So sample space is building out a 5-digit number, no restrictions. Now, very careful with 5-digit numbers because, or actually any numbers with digits, the first digit can never be 0 or you have a 4-digit number, right? So the first digit you can only choose from 1 to 9. Yeah, that first digit there. So there are only 9 ways to fill out that first digit. Then after that, it's 0 to 9 for the remaining digits. So 10, 10, 10, 10. Okay, so 90,000 is your sample space. All right, A, we want it to be at least 70,000. 1, 2, 3, 4, 5. So the first digit has to be 7, 8, 9 for it to be 70,000, above 70,000. So that's 3 ways to fill out the first digit. Now the question doesn't say you can't repeat, so I can assume repetitions allowed. So there are 10 digits to fill out the remaining. So that's 30,000. Okay, so the probability is 30,000 on 90,000, which is 3 on 9. Part B, odd digits only. So odd digits consist of 1, 3, 5, 7, 9. 1, 2, 3, 4, 5. So 0 is not included. So that's basically 5, 5, 5, 5, 5 then. So 5 to the power 5. So the probability is 5 to the power 5 on 90,000. Yeah, on the sample space, which gives you 643 on 18,000. All right, so the next one. The digits are distinct. Distinct means they're different, meaning repetition is not allowed. Let's do it here. All right, distinct. 1, 2, 3, 4, 5. Okay, so in that first digit, again, it can only be 1 to 9. So there are 9 ways to fill out that first digit. Now, you've used one of the digit, but you can now also use 0. So you have also 9 digits for that second one. Does that make sense? So because you have 0 to 9, yeah, you've used that one digit, so you have 9 digits. And then you have 8 digits if it has to be different, and then 7, 6. Alright, so that should give you 27,216. So the probability will just be that number over 90,000, which is 189 on 625. Alright, so part D, number contains at least one 4. So at least one 4, sorry, let me show you the question. At least one 4, when you see the word at least one, look at the complementary case, which is no 4s. Okay, so the complementary is no 4s. So think about our digits here, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. No 4s, can't use a 4. The first one you can't use a 0 either, so there are only 8 ways to fill that first spot. Once after that, you can use the 0 again, so it's 9, 9, 9, 9. So that gives you 52488. Alright, so the probability, because this is a complementary case, okay? So it's 1 minus the complementary case, which is 521 on 1250. Alright, so finally, number contains at least one 4 and at least one 5. Now that's a little bit tricky to count, and I'll show you why. So let's add another page. So at least one 4 and at least one 5, the complementary case is no 4s or no 5s. Now no 4s or no 5s is very tricky because there is a bit of an overlap between the two cases, yeah? No 4s, no 5s, and there will be a bunch of numbers that's got no 4s and no 5s. Okay, so remember the addition rule, right? So we've actually calculated no 4s. So no 4s is this one, 52488. Now no 5s will be counted in exactly the same way, so it's also 52488. Alright, so this bubble is 52488, this bubble is also 52488, and that middle part is no 4s and no 5s. So we can't use. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't use 4 or 5. Okay, let's count this. So the first digit, we can't use 4, we can't use 5, so that's 8, and you can't use 0 either, so that's 7, and then the rest is 8. So that gives you 28672. Okay, so that space there is 28672. Alright, so when you're calculating the number of cases where it's no 4s and no 5s, so no 4s or no 5s, that's equal to 52488 times 2, so 1, 2, but take away that double counting, right? Because if you double count, yeah, we've overcounted. So take that out. So 52488 times 2 minus 28672. So 76304. Alright, so the probability in this case will be, remember this is complementary, so 1 minus 76304 over 90,000, which gives you 856 over 5625. Alright, so that's it. That's the question. Alright, the number that contains at least one 4 and at least one 5 is just basically that probability there. All right, finally, let's look at the probability, but this time in a circle. So we've got a committee of 3 women, 7 men to be seated randomly at a round table. What is the probability that 3 females will sit together? Actually, before we do that, let's have a look at the sample space. So sample space is 3, 7, so 10 people. So 10 people is 9 factorial in a circle. That's your sample space. So part A, what is the probability that 3 females will sit together? So you put the 3 females together and then the 7 individuals for males. So you have 7 plus 1, so 8 elements in a circle. 8 elements in a circle is 1 less, so 7 factorial. And then the females, the 3 women, can rearrange amongst themselves, so that's 3 factorial, which gives you 30240. Okay, so the probability is 30240 over 9 factorial, which gives you 1 on 12. All right, so the second part. Okay, the committee elects a president and a vice president. What is the probability they sit opposite one another? So put the president down first. One way to put the president. Once you put the president down, vice president, one way, because it has to be opposite the president. And then the remaining people, it's just 8, 7, 6, 5, 4, 3, 2, 1. So the probability is equals to 8 factorial on 9 factorial, which is 1 on 9. Alright, so that's it. That's just one last example to show you how to calculate probability when we're dealing with arrangements in a circle. Alright, so to wrap this up, I'll give you a meme. You might find this interesting. So probability. If you watch Avengers, you'll know what this means. And that is it for this video. Hopefully you found it helpful. Now I know this is a tough topic for a lot of students. So if you have any questions at all, comment down below. I'll look at the comments and I'll try to answer you as best as I can. Now another thing I will also start doing is if you have any topics you would like me to cover, also comment down below and like the video so I know this stuff is good, and I'll keep producing these videos to help you guys. All right, bye now.